Okay, so we got a unique question. It's kind of a problem-solving question. It's asking, what is the coefficient of x to the power of negative 2 in the expansion of this binomial? We solved it by some guess and check. We went through the full expansion to solve it. But is there a more optimal way that we potentially can do this? Well, we can write out, we can do a little comparison to our general formula of a binomial, a plus b to the power of n. And we can try to fill in what information we have. So I happen to have an a value, that's x. I happen to have a b value, that happens to be negative 1 over 4, negative 1 over x to the power of 4, or negative x to the power of negative 4. We could also write it that way. And an n value we got is, looks like a b I've written here, but that's 13. That should say 13 there, okay? So what does that mean for our expansion? Well, our general expansion, we're essentially looking for, technically we're looking for the sum of something. Have you seen that, Val?
No, I haven't.
No? This means we're looking for, instead of writing out in the expansion where we have like first term plus second term plus third term, okay, blah, 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 all the way through to whatever the nth term is, that's what they would call it, the last one. We can say we're looking for the sum of a general formula. So our general formula happens to be n to our r value, n minus r. No, r minus n, n minus r. Yeah, it is our term value. So to the r value of a n minus r b r. This is like a general way of writing this formula. It looks very complex because there's a lot of variables involved. But we can use this to find a more optimal solution to this. So what we can start to do is, hey, we can plug in. We have an A, we have a B, and we have an N. Let's put it into this general formula. We don't need the summation part for this solving, so I'm going to leave it out at the moment. And we're going to leave it as a term value. I think you guys have written it like this, r plus 1, right? Yeah, so we'll say we're looking for a specific term value. And it turns out we are looking for a very specific term value. We're looking for the term value of when it's x minus 2. So we have this term value here with this general formula where we have n to the r, a n minus r, b to whatever r is in this case. It turns out n was 13, so we're going to plug that piece in. We have 13. R is unknown. That's literally what we're trying to solve. We're trying to solve for the r value here. A happens to be x. Maybe I'll write it in red so it's a little more familiar to what we're doing. Okay. The n value, again, we do know what that is. It's 13, but it's also minus r, which again is the piece we're unsure about. And then our b value happens to be negative x to the power of negative 4. I'm going to write it like that. It might be a little simpler this way. To the power of r. Again, something we don't quite know. This x here, and though that's a negative, these are actually like terms. This is a base of x, and this is a base of x. Really what this means, we can deal with our negative first. Like, hey, take a look at this. If I'm going to multiply these two terms, this is a positive times some negative. So we're going to end up with some negative term, assuming that this is an odd number. But what we can do is we can start to combine. So I'm actually going to common factor out this negative 1. And when I common factor out this negative 1, I have to be aware that that r is technically part of this negative 1. So that's a really tricky piece of this. I can actually take it, because of a rule of multiplication, I'm going to put my next line in negative 1 to the power of r. I've actually just common factored that out of this piece, so I'm going to make it a positive so that the bases look a little more similar to each other. So I have, let's do my combination. That's still a piece of this, 13r. This piece is still going to stay as x to the power of 13 minus r. This one is now going to turn into x to the power of negative 4r. That's that rule of a power of a power. We just multiplied the two together. Nice. Now I have bases that are the same. And we can use our rule of when we have two bases that are the same, we can actually just add whatever their exponents are and make it a single base. It's a simplification trick. So that negative 1, being able to see that we can common factor it out is a really tricky piece, but also pretty integral to solving this. So we have negative 1 to the power of r. We still have some combination, 13r. And this becomes a single exponent, or variable, I should say. X to the power of 13 minus r plus negative 4r. Okay. This little piece, I'm going to do some side math here. A little side of envelope here. 13 minus r. Technically, this is the same as writing minus 4r. We put this together. This ends up being 13 minus 5r. Okay, I can write that as a single exponent now. So I'm kind of going step by step, nice and slow, so we can see each of our transitions here. 13r becomes x to the power of 13 minus 5r. Okay, we've got this piece, and this is actually going to be the most important piece here, what we've done here. This is some coefficient, and this is some coefficient. There's actually no x's involved in this, so I don't really need this piece of information. And again, that's like a overview of understanding that actually this question is only asking me one piece. They want to know, when is it equal to x minus 2? Well, this is the only piece that actually deals with a variable. And we can see that there's no x in this piece and there's no x in this piece. So it's only this that we're going to deal with. So we're actually going to build a second formula out of here. And it's essentially this concept. We're going to put these two together. We're going to make this its own equation. So we're going to call this x to the power of 13 minus 5r is equal to x minus 2. In your functions course, have you guys talked about logs at all? A little bit. I can use the log. I can use a log to essentially simplify this. Your teacher, the fastest way they'll explain this to you is because the bases are the same, we can drop the bases, and now this question just looks like this. 13 minus 5r equals negative 2. Technically, there is a piece of algebra that we've used logs to simplify, but as long as you're okay with this concept, and it's the same idea. If I had 3 to the power of x is equal to 3 to the 3, well, I can just drop these 3's, x is equal to 3. That's the exact same thing that we did. We just dropped the bases off. Now this becomes like a linear equation in which I'm trying to find r. So I'm trying to find r here. Well, I can bring 13 to the other side. So I get 5, negative 5r is equal to negative 15. And then when I divide both sides by negative 5, it turns out I'm going to get r is equal to 3. R is equal to 3 in this case. Okay, so now this piece of information is pretty integral. We just solved what r is, which means to find the coefficient, let's jump back into this piece. This is the part that's going to help us find the coefficient, which is good because what we've actually done here is we've figured out how to separate this equation into the coefficient piece and the variable piece. So we dealt with our variable piece. It gave us some info. Now we're going to apply it to the coefficient piece. So I actually don't need the variable piece. I know it's going to be x to the power of negative 2. So let's deal with our coefficient. Our coefficient ends up being negative 1 to the power of, well, r happens to be 3, which is an odd number, which is actually going to be really important because it's going to determine whether this is a positive coefficient or a negative coefficient. The second piece is that combination. 13 choose 3. Not a number I know off the top of my head by any means, but you have your calculator, right? What did it end up giving us? 286. Awesome. So this part ends up being 286, which is positive, but this actually ends up being a negative 1. So when we multiply it, we get negative 286. And if we wanted to put everything together, we also know that this is what the exponent would be. So there would be our final answer. But again, what they wanted was just the coefficient piece. So this would be our answer. I don't know why it's so small here. That would be our answer to the coefficient piece. So in retrospect, to be dead honest, I still think the expansion of this might have been a faster way to do it than this algorithm we built. Again, if you know the algorithm off the top of your head, you might go, I can build this really quickly. But this algorithm is also seldomly used. So the expansion, assuming it's not too large of an exponent, it might be faster just to expand and solve a question like